Okay, so again, welcome to the seminar, the webinar from Kruse Training. My name is Torsten Kruse, and the webinar series is once a month, and this month we will talk about gate symmetry. I have prepared a lesson for you which we will be reviewing. So bear with me for a minute, and let's just talk a little bit about cause and effect behavior in injection molding. Why is this so important to know? So when we start out in learning in injection molding, um, we have to know a little bit more about the cause and effect behaviors in injection molding. Why is this so important? Uh, if you try to be um, very good in your job and trying to learn injection molding, it is very important to understand the polymer behavior, the part design, the mold design, and the processing. If you're trying to understand just one of the subject matters and you learn about plastics, or you learn about part design, or you learn about mold design or processing, it is very difficult to understand the entirety and the impact and the effect among each other. Basically, again, the cause and effect behavior injection molding. If you don't study all of it together at once, you will never understand the behavior between those factions: polymer, part design, mold design, and processing. It is very important to understand that. That's why we created what we call the circle of knowledge training. The circle of knowledge is basically taking into account all of these factions and trying to teach this behavior in its entirety. Okay. Today we will focus on the mold design, gate symmetry, and balance. And on the on the agenda, we also have a little housekeeping. If you like to ask a question, don't be afraid. Just send us a text message via the chat function. And when we have some questions, then we'll answer them after we are done. Okay, again, this is focused learning. What that means is we are having a focused learning effect, and this time on gate and gate symmetry and balance. Understanding complex behaviors and interaction in the injection molding industry is critical in order to stay competitive and ready for the future. That's definitely true. Yeah, if we don't understand the effects among each other in the molding business, we don't learn, we do not understand the behavior, and we have potentially a project that is not successful. So for that, we need some molded part requirements. When you start out, you need to know the critical dimensions and tolerances of a part you are trying to design, build a mold for, and process. You need to know a little bit more about the structural strength requirements of a part. That's important as well. Appearance and aesthetics, acceptable shrinkage and warpage behaviors, and of course the assembly functionality. Those are molding part requirements that need to be understood before you even start a new design project. If you miss one of them, you may have some challenges later on. And that's why it is so important to really build the circle of knowledge amongst your team. Involve the part designers, mold designers, the processor, and the material supplier to really understand each other's business just a little bit better, and that will lead to a much better outcome for the end product. So we have developed, therefore, an online training platform available 24 hours a day, 7 days a week. Our lessons are 15, 20, 25 minutes long. And there's a reason for it, because the intention span of a person is 18 minutes, and that's the reason why we do 18 minutes, because we want to capture your intention, but don't bore you, okay? So let's get started with the lesson on gate symmetry and balance in injection molding.
Gate placement is an important aspect of mold design. Part quality will be directly affected by gate placement. And this lesson looks at how gate symmetry plays an important role in achieving high-quality molded parts. In this lesson, you will learn the importance of symmetrical gate design in molding plastic parts, how gate placement affects injection pressure and packing pressure distribution, how fiber orientation is impacted by gate placement, how uniform fill behavior, fiber orientation, and packing pressure distribution can improve the overall shrinkages and flatness of a part.
So all of these aspects we'll discuss a little bit, but just think about every plastic part item you see in front of you. From medical devices to automotive devices, we have challenges with every injection molded parts. Wall thickness variations, where do we place the gate? The gate placement again has impact on the injection pressure, on the packing pressure distribution. Everything we do in injection molding will impact the quality of the part. What material are we using? How easy can we transmit the pressure throughout the cavity? Is it a semi-crystalline material? Is it an amorphous material? Wall thickness distribution. Do we have ribs? All of this will impact the quality of the part. And that's why it's so important to understand the cause and effect behavior between the polymer material and the part design. That's number one. That's first. If we understand this behavior, if we can optimize the part design based on the material, only then we should go into the mold design.
Injection molded parts should be designed symmetrically, starting with the part design and continuing through the mold design phase. Gate placement is an important part of this design process. Non-symmetrical gate placement can cause non-symmetrical fill to warp behavior, resulting in unacceptable part warpage. For this lesson, we will evaluate a part with 4 gate variations. The first 2 examples use a single fan gate on the main parting line of the part. The first gate example is in the center of the part, and the second is off to one side. The third and fourth examples are a single and dual gate placed into the top parting line.
So a very simple part. As you can tell, it's almost like a box type of a part with ribs. And we have 2 upstanding bosses here that we need to worry about. It's supposed to be very flat. And again, it's a very simple design. And gate placement here will play a role. We'll take a look at it in detail, okay?
The part is molded in a 30% glass-filled PPS material with a mid-range process setup and a fill time of 1.3 seconds. Beginning with the filling animation and injection pressure curve for the first example, there are no significant fill-related issues. The ribs, bosses, and skirts fill as expected. This first animation shows the bottom view of the part. The second animation shows the top view of the part. The pressure curve shows a steep rise as the runner in gate fill. Once the material passes through the gate, there is a smooth rise until the part is filled. The highest pressure at the end of filling is 109.5 megapascals.
So very simple again, how to read these curves. Every molding machine should be able to output these curves on a hydraulic basis. But on the bottom we have the time, on the y-axis we have the injection pressure. And I love these graphics because it really tells me what's going on inside the mold during the fill process. And we can tell this injection starts, we fill the sprue, we fill the runner, we get through the gate, and then we fill the part. Very smooth behavior until we reach the switchover point and flatten out because we use the same pressure during the pack process. So this is how you can read these injection pressure curves on your actual machine, and they tell me a lot.
The second design with the offset fan gate also shows the part filling without any fill-related issues. The injection behavior is the same as with the center-gated example. Here is the bottom view of the part, and on the next slide, you will see the animation for the top view of the part.
And again, it looks like a very smooth fill behavior. Sprue fills, secondary runner through the gate, very smooth fill behavior inside the part, reaching packer, switch over point, and flatten out the curve.
The offset gate required higher pressure to fill the mold. The maximum pressure at the end of filling is 128.5 megapascals. Here you can see the injection pressure images side by side for comparison. The offset gate's pressure requirement is 19 megapascals higher than the center gate. Although this doesn't seem high, it is a 17% difference. The gate offset creates an increase in the overall flow length from the gate to the end of the part. A longer flow length generally causes higher injection pressure requirements.
Again, very simple. If we offset the gate by just a little bit from this position to this position, all of a sudden the material has to flow, the flow distance from the gate towards the end of the part is longer. Longer flow distance, higher pressures.
Now we will look at the filling animations and injection pressure curves for the top gate setup. Beginning with the single gate, looking at the bottom view of the part. Notice there is a quick rise in the pressure at the beginning. This is because of the gate and runner sizes. The part design features fill without any issues. Notice the pressure curve has a small jump at about 1 second into the filling phase. This small pressure increase is because one side of the part fills first, and all the flow energy then has to be redirected to fill the rest of the part.
Yeah, so one more time. We now place the gate on the top of the part, and with a small, thin fan gate, yeah, or edge gate, fan edge gate. And that's the reason why this pressure jumps so quickly, so high. The part filling is very smooth. At 1 second, we see this little jump. And the reason for that is this side, the left side of the part is filled. Now all the material, energy, flow energy, has to be reversed or redirected to fill the remaining section of this part. That's why this spike comes in.
The highest pressure for the single gate example is 128.5 megapascals at the end of fill. The next two animations show the filling and injection pressure for the dual gate setup. Again, there are no issues filling the part design features. The immediate pressure rise is due to the size of the gate and runners, but once the material passes through, the increase becomes smooth and gradual until the part is filled.
I think you can tell this is a lot more uniform, isn't it?
The required injection pressure for the last example is 93.1 megapascals, which is the lowest of the four examples. Again, the flow distance will determine the overall pressure drop inside the cavity. Comparing the two pressure images side by side, you can see that the dual gate example not only has the lowest injection pressure requirement, but also the most uniform pressure distribution.
Yeah, you really can see this. I mean, a dual gate, you have blue, 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 and blue, and what does blue mean? Low pressures. Might as well with the single gate, you have the left side be pressurized during filling already, and therefore it's a little bit more uneven and higher pressures. So uniform pressure distribution inside the cavity will lower the required injection pressure in a molded part. Very important.
Now, comparing all four examples, you can see that the dual gate setup has the most uniform injection pressure distribution. The fan gate in the center of the part has the second most uniform distribution, while the off-center fan gate and the single top gate have non-symmetrical fill patterns and higher injection pressure distributions at cavity fill.
non-symmetrical pressure distribution not only during filling, but if you get into the packing phase, you still have non-symmetrical pressure distribution.
Because we are using a 30% glass-filled PPS material for these simulations, it is important to evaluate fiber orientation after filling. Let's begin with the X direction, which is the length of the part.
So one more question about the fiber, or one more explanation about the fiber orientation. In fiber-filled materials, we can visualize how the material is oriented with colors. So that's basically what you see on the screen is right colors. The color red really means the fibers are highly oriented in this case, X direction, so in the length of the part. Yeah, and we can see here very clearly that with the edge gate on the side of the part, we have some areas that are very highly oriented in this X direction. The opposite side wall is not as highly oriented in the X direction. We can tell from this center gate that we have highly oriented material near the gate, on the opposite side of the gate. But look at the difference in the side walls. Highly oriented, highly not on the surface near the gate. So we can basically tell and look at these graphs and these colors in the fiber orientation plots and can tell which one really looks most uniform. That's what we are looking for when we look at these fiber orientation plots.
Of the 4 examples, the top dual gate shows the most uniform X direction fiber orientation behavior. Moving on to the Y direction, or the height of the part, the dual gate example shows the most uniform alignment of our 4 examples. Lastly, let's look at the Z direction, or the width of the part. Notice here there are significant differences between the first 2 and second 2 examples. This is because the fan gate is positioned directly into the base plate, while the single and dual gates are set up on the top of the part. Of these 4 examples, the dual gate shows the most uniform Z direction fiber orientation.
Yeah, it's very clear. This is highly aligned in what we call the Z direction here, because the gate is here. So it has to be aligned. With the center fan gate, most of the material here will be aligned in the opposite direction in the X, but then aligned in the Z, like we have. This is pretty symmetrical, actually. But the most symmetrical one is the dual gate.
The next set of evaluations focuses on the packing phase. Here you can see the packing pressure for the first example at about 1 second after the switchover from filling to packing. The packing pressure range is from 109 to 5.3 megapascals. The lowest pack pressure is in the thin skirt sections on the gate side of the part.
Yeah, and this is very telling because in the packing phase, this is 1 second after we switch over from filling to packing. If we see a very low pressure here, that means this material is frozen or about very close to being 100% frozen. So what that means is you can't pack it out. Okay.
When packing pressure distribution is uniform, shrinkages will be uniform, which will result in a more dimensionally stable part. The packing pressure distribution range for the offset gate example is 128 to 7.2 megapascals. The lowest pressure, again, is in the thin skirt areas closest to the gate.
Remember what happens. Material flows into the very thin skirt. It tries to fill it. It slows down. It cools down. And it freezes. As closer this happens to the gate, usually as quicker it goes.
The single gate on the top surface shows a packing pressure range of 128 to 0 megapascals. As in the previous 2 examples, The lowest packing pressure is in the thin skirt on the gate side. The final example with the dual gates shows a more even pressure distribution inside the cavity. Here, the range is from a high of 92.7 to a low of 40.6 megapascals.
Much more narrow pressure range. And why is that? Yes, it is a lot more uniform in the fill pattern. The material gets to this thinner section pretty late in the fill cycle. Therefore, the pressures inside the mold are already a little higher. And because these thin sections get filled at a later stage in the fill cycle, there's very little freeze-off. That's why little higher pressure is second into the packing phase.
Here, in a side-by-side comparison, you can clearly see that the dual gate has the optimal packing distribution of the four examples. The material in the thin skirt section freezes quickly, so cannot be packed out. This is the cause of the low pack pressure immediately after the cavity is filled. In the dual gate examples, the thin skirt section fills last, so the polymer material there has a higher temperature, resulting in higher pressure in the packing phase. In the first two sets of evaluations, the dual gate example showed the best results. But does this guarantee better overall shrinkage and flatness of the part? Let's take a closer look at the Y direction warpage behavior for the four examples to determine the answer. As a reminder, the material for this lesson is 30% glass filled. Anisotropic material shrinks less in the direction of the fiber and more transverse to the fibers.
That is very important to remember. Anisotropic properties shrinks less in the direction of the fiber, shrinks more transverse or 90 degrees to the fiber. And now we remember the fiber orientation images I showed you. That's why it's important to understand how the fibers are oriented, because they will impact shrinkage and warpage.
This animation shows the Y direction warpage for the centered fan gate. All four corners are warping upward by about 0.55 millimeters, while the center is warping downward by about 0.21 millimeters. The warpage behavior for the offset fan gate shows less uniform behavior than the previous example. Because of the fiber orientation, you can see two of the diagonal corners are warping less than the other two. But notice the blue corners are warping upward by 0.94 millimeters, almost twice as much as the previous example.
The part is twisting. Lower warp corners, higher warp corners. Everything is due to the fiber orientation.
The next evaluation for the single top gate example again shows non-uniform warpage behavior. The two corners that fill last have the highest warpage of almost 0.94 millimeters. The uneven fill behavior results in uneven fiber orientation and therefore non-uniform warpage. The dual gate setup shows minimal part warpage, with the two corners warping upward by only 0.18 millimeters. Most of the part is below the 0.07 millimeter flatness.
As you can tell, it is also uneven, but the amount of uneven warp is still very, very low compared to the uneven warpage we've seen with the other gate options.
Here you can see the warpage results for our four examples. Earlier, we asked if uniform fill behavior, fiber orientation, and packing pressure distribution could improve the overall shrinkages and flatness of the part. According to these results, the answer is yes. The lowest part warpage is with the dual gate setup into the top of the part. Although the centered fan gate has greater warpage, all four corners are warping to the same degree, versus the off-centered fan gate and the single top gate. This concludes Section 4, Mold Design, Gates, Lesson 10, Gate Symmetry and Balance. In this lesson you learned the importance of symmetrical gate design in molding plastic parts, how gate placement affects injection pressure and packing pressure distribution, how fiber orientation is impacted by gate placement, whether uniform fill behavior, fiber orientation, and packing pressure distribution can improve the overall shrinkages and flatness of a part. Designing and molding high-quality parts starts with optimizing part design and gate setup. Symmetrical gate placement and gate sizing has a significant impact on molded part properties and flatness. Once a part design is optimized and proper gating is determined, the mold design can be optimized, resulting with a less challenging processing step. By checking off each of these steps in the injection molding workflow, successfully molding high-quality parts can be achieved.
Okay, very clear, very simple, very precise, very focused. That's what we try to do in our lessons. And it was a very simple lesson, but a very powerful lesson that when trying to gate a new part, you really need to evaluate all options. There are simple options for tool design reasons. There are more challenging options to integrate into a mold, but often it is important to look at the overall behavior from filling, the distribution of the pressure, the fiber orientation, the packing pressure distribution. All of that will impact the part final shrinkage and warpage behavior. Doing this up front, of course, it's easier than after the first mold is built and the wrong gate location has been chosen. So I can only encourage you to learn, to evaluate, to optimize, and then go into the production of a part after the part design is optimized. The circle of knowledge. Part designers, mold designers, processors, if they all understand this behavior just a little bit better, we believe that a lot of molding challenges can be avoided. If you have any questions, let us know. Otherwise, you're always welcome to send us an email, please. And we are here to help. You have the email on the screen, Thorsten_Kruse@krusetraining.com. This will be on our YouTube channel for you to review in a few days. So check our YouTube channel through Kruse Training and you will be able to review this lesson again. Let's see if we have any question. Is there any effect the number of gates on the filling time? In general, when you talk about the number of gates and the effect on the filling time, when you have a single gate, you have to inject material through one gate. If you have one gate, the shear rates through one gate will be higher. Therefore, the viscosity of the material will be lower. A dual gate, when you injected material in the same time, basically the shear rates are reduced in half. That means the viscosity will be a little bit higher. And usually the injection pressures would be higher, but because you have two gates, you maybe cut the flow length of the material inside the mold, and you can actually lower the amount of pressure required with the dual gate. Important is, as you can tell, the number of gates need to be adjusted based on the part design to optimize the flow behavior to create a uniform fill pattern. That is really, really important. Okay. All right. So thanks for all for your time. Again, this recording will be available very soon on our YouTube channel. And stay tuned. Next month we have another one. And again, if you have a question, don't hesitate to email us. Okay? Take it easy. Have a good day. Bye-bye.